one of the things that excites and fascinates those of us that work in the field is that the physical principles that underlie superconductivity are completely different than those in the semiconductor electronics. And this gives it some unique characteristics that allow applications which are different than you would associate normally with semiconductor electronics and very broad. They range from the high-speed characteristics, switching characteristics, which could be useful in communications or possibly in computation. There also is a whole range of very sensitive measurement instruments that can be constructed from superconductivity and superconductors.
The key component of any digital communication system is the analog to digital converter. Hypers uses a revolutionary approach to make analog to digital converters that can be placed directly behind the antenna. These devices provide up to 20 effective bits of resolution and over 100 dB of spur-free dynamic range on signals of bandwidths up to 2 gigahertz. Our next generation technology, which is already under development, can provide up to 24 effective bits and over 160 dB of spur-free dynamic range. This is performance like no one has ever seen before.
The analog to digital converter is only one of a whole range of circuits that enable us to make a complete digital RF transceiver. These include a digital to analog converter, ultra-stable multi-gigahertz clocks that will enable us to make spectrally pure carriers, digital mixers, and digital signal processors.
This high performance is possible because our technology can build virtually noise-free front ends with orders of magnitude better sensitivities than that of conventional receivers and bit error rates of the order of 10 to minus 15 even for the widest signal bandwidths. These devices are so sensitive that we use them to measure brain currents.
Our technology produces circuits that are fast, low power, and are essentially noise-free. We switch in picoseconds. We dissipate only milliwatts per chip. We have bit error rates of less than 10 to the minus 15th. Using these rather remarkable features, we can produce very high-performance electronic switches for the fiber optic backbone.
By going to 40 gigabit per second and then to 160 gigabit per second, we increase the data rate per wavelength and will require fewer wavelengths to cover the entire bandwidth. This results in significant reduction of optical hardware by about an order of magnitude.